Ladies and gentlemen, Todd.
See him after this.
Yeah, I'll take issue with both of you later.
Quiet, Beardy.
Hi. Okay, good volume. Am I being loud enough?
Yes.
Thumbs up.
All right, cool. I'm Todd, and I'm going to talk about the new storage engine that's coming out with v0.10. It's in the RC right now. I don't know if any of you guys, actually, has anyone tried it yet? 1, 2. Michael, you don't count. So anyway, I basically am going to cover the storage engine, some stuff about it, kind of how we got to where we are now, and how we tested it. So thank you, Ben, for all the animations on my slides, by the way. What is a storage engine? It's kind of a nebulous thing. You hear it. You know every database kind of has one. But what is it really? So basically, the storage engine is the piece of the database that determines how the data is stored on disk. So there's a data structure that's kind of inherent to every different storage engine. Whenever you're looking at compression characteristics, that's all part of the storage engine. And specifically in InfluxDB and other databases as well, the storage engine is what defines sharding, how data is distributed across different files on your operating system. And all this is kind of inherent to the design of each individual storage engine. So at a higher level, as you're looking at the rest of the database, the storage engine is what gives the rest of your code a read-write interface to what's on disk. So you give it points in InfluxDB, you ask for points when you're issuing a query, and the storage engine is what deals with making sure things get persisted and making sure that things get back to you when you ask for them. It also handles indexing, so the indices that InfluxDB uses and basically in every other database are part of the storage engine. So those are kind of how it actually finds the data on disks without having to actually scan through everything. Indexes are there for fast lookup. Usually there's a caching layer involved in the storage engine, data that's either stored in memory to be looked up quickly. It could be the most recent data or the most frequently used data. And overall, the storage engine is kind of what defines the basic performance characteristics of the database. So I've got some examples here. These are basically different storage engines that are part of the MySQL family. So MySQL itself, there's MariaDB, which is actually a fork of MySQL that's drop-in replacement. Percona for a while was also working on other storage engines. So each one of these is InnoDB, ISM, Falcon, ExtraDB. These are all different storage engines that all work inside of MySQL and its variant databases. And each one of them is designed to have different read-write characteristics and be better at certain use cases. So each one of those still gives you the same functionality inside of MySQL in particular as a relational database, but they're designed for different things, have different compression characteristics and such. So why would we build a new storage engine for InfluxDB when we already had one that worked? The benefits of building our own storage engine are that what we're doing with InfluxDB is special. It's time series data, and the use case matters. So just like with MySQL, there are reasons why you would want to have variations for a relational database for different kinds of data. For us, we wanted to build something that was specifically designed for time series data. The reasons why time series data is special, and I know Paul's given many talks about this, but you don't really have updates. You're doing a lot of high volume inserts, and it's usually append only. If you're removing data, it's usually only old data, and you're usually doing it blocks at a time. You're not doing individual deletes like you would be with a relational database where you're deleting a single user or a single record. Very high throughput requirements. If you're using it in a production system, you're going to be collecting data constantly, and it's really never going to change. So you need something that can keep up with a high write load and not build up a backlog of data. So you need something that's designed for that. And this is something that I'll get into a little bit more, but because of time series data being usually you're measuring something, whether it's a CPU value or a temperature or what have you, it's usually a value that from measurement to measurement changes slowly. So the underlying value is not going from 0 to a million and back to 0. It's usually something that's a floating point number that's just varying slowly over time. And the upside of being able to do our own design kind of lets us use our own index structure that makes it easiest to work with our query language, with our just kind of internal design. So a lot of things that we can do to make it work as efficiently as possible with the way we want to use it. And then once we have something like we do now with v0.10, going forward, because this is our code base, this is our design, it lets us kind of keep tuning things as we find places that we want to be more efficient, as we find places that we either learn more about how people are using it. We've got a design that we can kind of build on easily to optimize in the future. Okay, so a little bit about what makes TSM special. So TSM stands for Time Structured Merge Tree. And this is kind of a naming that's borrowed from the log structured merge tree, but what we're doing is basically working around blocks of time as our kind of underlying format. So it's a column-oriented storage engine, and as Michael just said, the current version has an unlimited number of fields. So basically there's not a 255 field limit. Per measurement, you can have as many, per series, you can have as many fields as you want. Depending on what data type you're writing in, whether it's integers, floats, strings, booleans, we use an adaptive compression. So it's not just a single compression protocol that we're applying to everything. Everything gets handled a little bit differently depending on what it is. And that's for both timestamps and values. So there's some logic in there that looks at if you're sending values every minute or every 10 seconds, there's some advantages we can take knowing that the interval between timestamps is consistent or is close, so that we don't have to store the entire 64-bit timestamp every single time. There's a background compaction process that's always running. So as we're collecting data and writing it to the TSM files, there are those optimizations we can make over longer running periods of data that we can compress to get better rates of compression. So basically, similar to what you'd have with an LSM tree, where you kind of have, level DB is a good example, but you have an increasing level of compaction, and the data files get larger and larger. And what we're doing behind the scenes is taking smaller files that are easier to write, and we're compressing them as they're less frequently used and getting better and better compression. So over the long term, we're moving towards an optimal compression for the entire TSM file. There's a built-in write-ahead log. It's different than the one that was there with 0.9. It's faster, and it's also got an in-memory cache that's queryable. So as you're writing data in, even if it's in the write-ahead log, it's still available for queries even before it actually makes it to the final storage layer. And that's also persisted on disk. So once a write is accepted by InfluxDB, it's written into the wall, and even if you shut the server down, that will be written to disk, and then when you start it back up, the wall files will get read and then flushed to the storage engine. So you basically, once you have a write, as long as you don't lose the data on disk, those are durable. And then, as Michael was kind of describing, you have the measurement and the tag set, and each one of those series has a unique index inside of the storage engine. So doing a lookup on a measurement and a set of tag key and values, that is a single location inside of the storage engine, so that we only have to go to that one spot. There's no seeking or anything like that if you're looking by tags. Okay, so kind of where this talk was headed was, building a storage engine is complicated. What are the things that you kind of need to consider? What are the things that we need to test? We're talking about storing a lot of data over a long period of time, and this thing is going to always be running anytime you've got a production system. So what are the things that we thought of testing to let us know that this thing is actually working right? So there are a lot of things to keep in mind. This is definitely not an exhaustive list, but these are just kind of the top of the mind things that really matter. So the most obvious one is accuracy. If you write data in, is that what you get out? That's on the easier end of the spectrum to test, but it's something that's important, and it definitely matters, even as you're doing data compactions and things like that, making sure that the data doesn't get lost in any way. Throughput, something that people always ask, how fast is it? How quickly can we get data in? How quickly can we get it out? Compression. So this is something I'll touch on a little bit more and kind of compare some of the previous storage engines that we used in 0.8 and 0.9, but kind of look at how good can we do? Like, what's the best we can really do, given that every point has a unique timestamp and at least one value? How much memory is required? So if we have indexes, those have to be stored in memory. What is the memory footprint that's required, and kind of how much can we do to optimize that? Failure testing. If you are in the middle of writing data, if it's in the middle of a compaction and either it dies or you kill9 it, what happens? Like, is it recoverable? Does the data get handled gracefully? And just what happens when things go wrong? And then some scale testing. So what happens as the data set grows? So we've got indexes that need to be loaded in memory. What happens if you have 100 gigabytes of data, a terabyte, 10 terabytes? What do these large data sets look like when you have to bounce the system? Because if you have to wait hours, which was actually something, I don't know if anybody ever ran into this with v0.8. Yep. So, you get 100, 200 gigs of data, and sometimes LevelDB just decides to do a lot of scanning at boot time, and you bring the system down for an upgrade or whatever, and you end up waiting a very long time for it to come back up. So it's something that we're very aware of, and especially as you get to larger production deployments, you want to be able to cycle nodes, resize, whatever it is, and you don't want to have to spend an entire day waiting for it to come back online. Okay, look back to the past. Influx 0.8. So when we were first building InfluxDB, the storage engine was probably the more complicated piece of what we were trying to tackle. A lot of it was kind of like revisions on a proof of concept, looking to see how it worked. So we kind of looked at what was out there. LevelDB was kind of an obvious choice. So we started moving forward with that, and then people asked for more variety. There was RocksDB, HyperLevelDB, which are both forks, and then LMDB, which is not. It's a different architecture, but similar key value store on disk. So we did some benchmarking, and there's a very old blog post from middle of 2014 probably, where we kind of looked at some of this stuff and ultimately ended up deciding that RocksDB was kind of a better choice, and then ended up reverting that decision later for a variety of reasons. So the things that we didn't really kind of know getting into it, but didn't seem like a big deal because Go works well with C. Sure. So all these were written in C and C++, which meant that you were using CGo, but you were pulling in some non-Go code. For better or worse, it worked then. There were no secondary indexing capabilities. These are just like plain key value stores. So we were kind of building our own keys from the timestamp and the series that we were writing. And because these weren't really part of our code base, we're not just going to go make our own fork of LevelDB and start customizing it. So it's kind of like we're dealing with someone else's project. It's not Go. It's not really our forte necessarily. So there's a limited amount that we can actually do to change the architecture of these and customize it for our own needs. So we kind of took with what we had and ran with it. And this was there was some naive benchmarks that we ran, but just essentially seeing how many points can we get in and out, storage on disk, all that stuff. So this is kind of where it stacked up. RocksDB, as I said, ended up being the fastest just in terms of points that we could get in. It ended up being a little bit bigger on disk than LevelDB, but for the most part, it was faster, and it seemed like that was the thing that got us what we wanted at the time. So LMDB, which is Lightning, it's Howard Chu's thing. I forget what Lightning Memory DB something. But anyway, so that was the one that was a different source code, and it's a B+ tree instead of an LSM tree. So it's a very different architecture. And I'll get into a little bit more of what we ended up going with 0.9. But basically, that one ended up not really working as well, wasn't as performant on reads or writes, and had a larger on-disk representation. So this was just kind of like ballpark, 75,000 writes a second, somewhere on the order of 500,000 reads per second. And again, these are naive. This is just like throw it on a MacBook Pro, run it, see what happens, and that's kind of where we came out. And this was with 100 million points. So this was over like a fairly long interval. I think it took on the order of 10, 15 minutes or so to write the entire data set for the test. So that's kind of how things stacked up with 0.8. So going into 0.9, there were a variety of things that we learned from 0.8. Again, we kind of wanted to get to a pure Go code base for a variety of reasons. Contributors had a hard time compiling in the C dependencies. We also had Lex and Yak for the parser. So just like getting everything to play together nicely ended up being a huge pain, and I think limited the amount of contribution that we could have because some people just gave up at that step. And aside from that, we kind of wanted something that we could start making part of our code base and optimizing. So we started moving into a direction where we were using BoltDB, which is basically just a pure Go B+ tree written by Ben Johnson, who's on our team. And as I said, having a pure Go code base was something that was really important to us just for making this a more community approachable project. And this was where we moved away from having a single series name that was essentially just like a concatenated string, and we moved towards having the tag supported natively. So this was something that was kind of part of the new 0.9 design. It gave us that. And we ended up with, across the 0.9 series, two variants that we experimented with. The first was just plain BoltDB key value store, and we handled the tags and stuff kind of internally and just used Bolt to kind of serialize everything, keep it as simple as possible, and that was okay. But we ended up seeing some performance problems with the B+ tree, which is actually similar to kind of some of the stuff that we saw with LMDB over here, which was a similar architecture. Didn't put it together quite until later that the design wasn't exactly giving us what we wanted, but ended up moving towards BZ1, which was essentially using compressed blocks of data associated with an individual key. So rather than a single timestamp series combination with a single value, we were moving to a timestamp that kind of pointed to the beginning of a block and then compressing that. So we actually got slightly better compression, different performance characteristics, and kind of ended up actually causing some more problems along the way. But it was an interesting learning experience because this was it was experimenting with these designs that sort of moved us in the TSM direction, and kind of got Paul working on the original proof of concept that got us to TSM. The biggest problem with these designs is that with the B+ tree, you're building a tree, and then as you start inserting values into it, you split blocks and add children to it. So you end up having to occasionally rewrite large chunks of the tree depending on how your insert patterns shape up. One of the problems with this, especially as we started moving to compressed blocks, is that means you end up having to rewrite sometimes large amounts of data, which ended up being very demanding on IOPS. And for people who are running on spinning disks where their IOPS is very low compared to SSDs, you start to see some very bad performance behavior, and essentially this becomes the limiting factor of the entire system. As I said earlier, your choice of storage engine determines how your database is going to perform. So in general, this wasn't always true, but we didn't really do better than the performance we saw in 0.8. So we got about 30 bytes per point on disk, which wasn't bad. It was kind of in the same neighborhood, but in terms of read and write throughput, really wasn't really a winner. So enter, actually, let me show you a graph. So up here at the top, this is during a write, basically a sustained write load. So you guys can't read the axis there, but that middle line is 10,000 IOPS. And most spinning disks kind of top out around 500. If you're good, if you're on a RAID array, you might be able to get a couple thousand. So basically, unless you were running SSDs, that IOPS load was unsustainable. So essentially, you would end up just getting totally backed up on your system. If you're running EBS, getting 10,000 provision IOPS costs a fortune, and is not necessarily even the thing that you want to be guaranteeing the stability of your system on. So the problem is that was essentially the level we were running at. And you see this part kind of here in the middle where it drops off, where either you get bound on I/O, CPU gets backed up. It really isn't good. And then the short-term load, it's relatively flat. So this third one here is CPU. It's kind of spiky. It's not so great. And then the bottom one here is resident set size of the process. So kind of does a little bit of spiky stuff. You're going between about 60 gigs down to 10 and back up again. So there's just a lot of in and out of memory behavior as it's trying to handle all this stuff on disk. Not really what we want. We'd like something more stable. What's that?
Are these stats that you can subscribe to?
So some of this stuff, so have you used Telegraph at all? Yeah. So some of this stuff, I think this was actually collected using collectd, but almost all this same stuff you can get from Telegraph if you're just looking at the I/O from the system. Okay. So talk to me a little bit more if there's stuff that you're looking for that we can try and figure out. But yeah, this is all either collectd, Telegraph, anything that's collecting system level metrics should be able to provide you with pretty much an overview of this stuff. So leaving you with that thought, how did we start testing TSM? What were the things that we did to kind of look at this new thing compared to the old one and make sure that what we're doing is actually better and more usable going forward? So we did a few things. There wasn't really a good way of doing synthetic load testing with 0.8 and 0.9. So we started building a tool that's now part of the Influx package called InfluxStress. Michael's done some work on it. It's kind of been passed around through the team. But now it basically takes a config file, lets you specify some parameters for what kind of data you want generated, lets you interleave queries at the same time, and essentially lets you run just sort of like an automated stress test to do a certain data set. And we used a combination of both physical machines in the server room back there and some virtual machines on DigitalOcean, on Amazon, looking at SSDs, looking at EBS, trying to find just as many patterns as we could to test against. And we did a bunch of long-term tests, writing data while retention policies are kicking in. So you're kind of getting like a stable amount of data over time, as well as doing full-scale write tests, just writing data as fast as possible and looking at memory usage under different series cardinalities and things like that. I think there's a GitHub issue that has some detail about TSM, but essentially we put together a bash script that just repeatedly kills the process and starts it back up again while influx stress is running in the background, just to make sure that there's never a time where we lose data. There's never a time where even during a compaction that the process becomes unrecoverable and won't start back up because of corrupted data. So as many things like that as we could think of to throw at it, where just make life hard and make sure that it handles things, because the storage engine should be the thing that's the most stable out of all this. And then, as I said, testing retention policies, doing queries, doing deletes, all while writes are happening, because even if you're pushing the write load to 100%, you want to make sure that you're still able to perform these other functions and have the database work as expected. So a little bit of performance stuff about what we did find. So this, on the other hand, is what TSM looks like. So this line here is I/O. So basically, that line right there is centered around 170 IOPS. And this is for maximum write load. And this is close to what you would see now if you tested the current version. These graphs are a little bit old, but the design was the same. So basically, what you want to see is something that's low enough that you could theoretically sustain this on, let's say, like a RAID array of spinning disks. If you're limited to 1,000, 1,500 IOPS, as you would in a lot of data centers, we want to make sure that that's something that we can actually physically accommodate getting the data that you're writing in to disk back out without having problems, because otherwise you're going to end up getting backed up. On SSDs, this is maybe 1% of the total IOPS that most SSDs are rated at. This second graph here is actually the disk used. So this sawtooth pattern is something that you'll see if you start looking at the way that TSM performs. So essentially, as the data is going up, you're writing data to disk, and then when compactions kick in, you actually see the data drop back down. So you're writing data in, compaction kicks in, that's what I was talking about. So you take the TSM files, they get recompacted, and you start to benefit from the optimizations of the compactions on larger data, so you get better compression. So you kind of see as it's going along, you get better and better performance. And this was one where we're actually throwing data away periodically as well. So you can see like a nice steady pattern. You see the compactions kicking in. You see that it's, the compression's working well and data is being safely stored on disk. This line here is load, looks pretty stable. And then the bottom one is RSS again. So basically, rather than having lots of huge spikes down to 0 and back up to full memory utilization, you're kind of seeing a similar pattern to what you see with the sawtooth on disk. And that has to do with how the data is being held, and as the compactions are happening, stuff is being evicted from memory, and you're seeing that it doesn't just grow unbounded. The indexes are actually getting well maintained, and as data gets purged, things get purged from memory. So this is basically exactly what we want to see all the time, and is kind of where we ended up with TSM under full write load.
That also had retention.
Yeah. So this one this one here has retention policy kicking in. So you see the disk used stays relatively flat. So there's the sawtooth pattern as data is getting written in, but it's essentially purging data periodically. It looks like maybe, every hour. I think there's, so these lines here, I think 2 hours apart. So I think every hour data was getting thrown away. So you kind of see the consistency. This graph, on the other hand, so we did a test of 50 billion points. So this took, day and a half or so to happen, because we're, it's a decent amount of data. Ended up being about 100 and something gigs on disk. So you see the load really nice at 7.5, pretty much all the way through. No big spikes, no big drops. And then this bottom one is just the disk used. So hidden in that seemingly straight line is actually that same sawtooth pattern. If you get really close, you can see it. But essentially, this is with no retention policies kicking in. This is just writing data as fast as possible to a single node. Question?
What's the batch sizes that you guys are writing those in?
5,000, I think, is usually.
In 1 second, was it like less than 1 second intervals?
I think this is just writing 5K batches as fast as possible.
50 billion, yeah, it's great.
Yeah, and I think this is with this is with like 10 concurrent writers, I think. So in the influx stress tool, you can actually specify a concurrency. So somewhere around between 10 and 20. I think Michael might have a little bit more. Yeah, 10's usually pretty good.
And 5,000.
Yeah, if you're doing larger batches. So you benefit from lowering the like network overhead and HTTP overhead of doing larger batches, but it means the concurrency can't go quite as high. So if you're doing smaller batches, you could get a little bit more concurrency. So basically, this is just CPU pegged, writing data as fast as you can, and yeah, 50 billion points in, yeah, I think it was about a day and a half. So what that means is that if you do the math, it ends up being about 350,000 writes per second. And I think that one was on just like a quad core CPU, nothing fancy, just writing to a generic SSD. So that's sustained. That was writing that data that entire time. Basically, like it's consistent. And the upside that we're seeing is that the storage engine is able to ingest that much data, write it to the wall, flush that to the storage engine, and then keep compacting that and keep that amount of throughput going all the way through all the compactions. So with a query, if you're just doing something simple like a count, where it's actually scanning through the points in a series or points across multiple series, on 09, on the code base before, I guess let's say the code base that's out right now with the RC, you should be able to do about 300,000 points per second scan. So if you're just doing a count, that's about how fast it will go through the data. So you can, extrapolate that out if you want to figure out how long it's going to take you to count 1 billion points. With the new query engine work that we're doing, that should come in 011. We're currently getting 2 million records per second. So that's essentially getting to the point where we can scan off disk as fast as we can read, and do the counts on that. So that's basically, no arithmetic overhead, nothing fancy, just doing like a count. So we'll be able to probably get some better performance optimizations with that as the new query engine comes online. So the math on this is that if you do 50 billion points and it ends up being a little over 100 gigs on disk, we're looking at 2 bytes per point. So get in your head the thought that like the timestamps that we're dealing with are actually 8 bytes natively. So they're 64-bit timestamps plus a floating point value, which is usually 8 bytes, 10 bytes. So you're looking at that much data is actually compressed down to be able to store 2 bytes on disk, and that's using all the encoding schemes that we've got in compression. So we're using delta encoding for floats and timestamps. I don't think there's anything else out there that can actually get close to that level of compression. I think Graphite's around 12 bytes per point. 12? Yeah, and then for reference, I can go back if you want, but the previous ones were 20, 30 bytes per point. So we're looking at, at least a 10x improvement. Depending on the data set, it could be even better.
That includes all the metadata about what measurement it is, what the tags are, all that stuff's included in the 2 bytes per point number.
Yeah, so sorry, question?
These stats are for bare metal?
Oh yeah, this is a bare metal, but even if I run it on a VM, it's pretty similar. Yeah.
You can get better than that on like an 8XL on AWS. You can do more than 350.
Yeah, and there's some stuff, if you're, depending on what configuration you're running in, it might make sense for the wall to be on an SSD if you're running on AWS.
Retention on this.
Yeah, and then everything else on like EBS or something over the network. But we're still playing with some more of that stuff. This is at a place where we're happy with the performance. It's stable. We're excited about all this stuff, but there's still a lot more we want to do to kind of look at like what it looks like on different architectures. Kind of how do we guide people in different environments to get like optimal performance. So we'll probably be publishing more stuff over the next month or two as we get more of this stuff tested, and especially once a new query engine comes online, we'll have more benchmarks around that stuff as well. So as I mentioned, crash stable. We haven't actually in any of our testing seen an instance of either losing data or having the system go down, even with full disk, where you actually could get the data store into an unstable state where it was unrecoverable. So that's pretty fantastic. And then, as I was mentioning about one of the startup time questions is how long does it take to load indexes off disk? So we're doing larger scale testing now, but right now with that 100 gigabyte data set that I was looking at, and I think I'd actually spaced it out so it was over, it ended up being data over several years of time. It was kind of synthetically generated, but that starts up in about 60 seconds or so. So we've done some optimizations to kind of make it so that the files get loaded in parallel. Everything comes online basically as fast as it can get loaded off disk, and that's just for the index, which is at the beginning of every TSM file. So that's quite a bit better than 0.8, and there's still probably more work we can do there, especially with like older shards don't necessarily have to get loaded at at boot time. We can kind of load the ones that we know are hot for queries, and then start the system up, load the other ones behind the scenes. So there's more stuff to do there, but that's within the range that we were wanting to get to. So with all that in mind, what's next? So one of the problems that we do know about is if you have super high series cardinality. So if you have like 5 million, 10 million unique series, the writes are not as high, primarily because you can't write enough points to each series per unit time to actually get enough data in there so that you're compressing it. So if you're looking at 10 million unique series, it's going to take you, even if you're doing 500,000 points per second, it's going to take you 20 seconds to write 1 point for each series. So if you're looking at the amount of time it would take you to write points, that you would write enough points that you would have a compressible data set, it takes you minutes before you can actually get enough on disk. So as the TSM files are getting created, you have a lot of just distributed points. So we're looking at some ways to handle that, to make it a little bit more efficient. It's not a very common use case where you have 10 million or more unique series, but it's something where as you have more dynamic data sets like Docker containers and things like that that are getting started up and shut down, and you're creating series that are eventually getting destroyed or no longer getting written to, we want to be able to handle that. So some of that is just experimenting with alternative index structures to make things more efficient. And as I said, moving some of the data out for series that go cold. As you saw, so that was I think that was a 4-core box. So I think it was pegged like right around 7.8 on the CPU load. So we're basically maxing out the CPU doing writes. And when you're not I/O bound, there's always something that you can do to make it a little bit better. So we'll be looking at more room for optimization. No promises on where we'll get, but we definitely think we can do better just in terms of write throughput and read throughput, as I said, with the query engine. Another thing that we had kind of been talking about is just doing a dictionary index for strings. So if you have a lot of string values that you're writing and they're repeated, rather than trying to store those all individually, just finding an easier way to look those up for better querying. And as I mentioned, better query engine coming in 0.11. I can make that promise, right?
Yes.
Yeah, okay. It'll be in 0.11, which we haven't set a date yet for, because 0.10 isn't even out yet, but 0.10 should be a week or so out, and then 0.11 not too long behind that. So that's what's coming up. Questions? Yes, sir.
Sucker question. When you write to disk, do you sync it, or do you async write and then?
I think we do an fsync after every write.
We do an fsync.
Yeah.
The wall gets an fsync after every write. One option we may add in later is to make that optional. So what that does mean is you get optimal performance when you do batching. If you were only to post a single point per request, like one, you have the HTTP overhead, that sucks. And then you'd be doing an fsync on every write, so you'd be limited, like probably do a couple thousand points per second if you're doing 1 point per.
Right.
Yeah.
That makes good sense.
So repeating the question for the video, I don't know if is that good form, Jimmy? Yeah. So the question was, how do we sync to disk between writes? And yeah, we basically do an fsync after each write. So on smaller batch sizes, there may be a performance penalty, which we'll look at maybe making configurable for later. But as long as you're doing larger batches, in the testing that I was doing, I turned that off, and it didn't really make a huge difference for the 5,000 point batches. So you're already writing it to disk basically as soon as it's coming in, anyways. So taking it out didn't really matter that much. Cool? I just quieted the entire room. I think I talked too long. All right.
No storing.
That's good. No storing. Thank you.